What is a number anyway? You might give me 1, 2, 3, 4, 5, 6, but what you don't know is that that's an instance, not a definition. You have no idea. I have no idea. We're going to figure this out. First off, huge respect to you for clicking on this content because honestly, most people don't care what a number is. They just use them or don't. If you don't know what a number is, it's a pretty easy excuse to tip your waiter less, to not care about um any your taxes or whatever. You can just say, oh well, didn't know what a number is, can't do math, sorry, didn't pay enough taxes this year. You hear me IRS, and they'll be like, oh, it's cool, I totally get that, I don't know what a number is either. So very easy to be uneducated, to just be watching your little TikToks, little Instagram reels, some Visco shorts, maybe. I just combined a platform and a name for short form content. I don't know if that's a real thing, but it just shows, obviously, if you do know that that's a real thing, or if it's not, that you knew about Visco shorts and decided instead to watch this. And that shows that you are prioritizing education, entertainment, and breaking the trend of your peers. Shows that you are directing your attention and action towards a great goal of education. Huge respect to you for that. Big fist bump. And my promise is that by the end of this video, you'll be able to define a number more coherently than two of the top mathematicians of all time, Bertrand Russell and Giuseppe Peano. Hands down, great mathematicians, but you're better. You're a better one. So hear me out, and you'll be able to get that. I'm Tommy, and CTMU Singularities, where your self-improvement meets a mindset of absolute truth and self-education. I help young guys get so self-actualized that they start figuring out the meaning of the universe. Subscribe right now and click that bell for more. I just said click that bell. I don't even know what the bell is. I've just heard that from other YouTubers. I think it's like the notifications big. So click that notifications, get notified, learn what school won't teach you. And yeah. And the point of this lecture is that when you just can see the within of things, you can easily discern there without. So with mathematics is always focused is linearizing or confining things to outputs, looking at their external relations, how things relate to one another, whereas the CTMU is all about internal structure. How do things relate to themselves? And so there are two methods of mathematics, ectomorphic and endomorphic. One is like standard mathematics, taking its shape from without, from these static relations, and one is from within, from this dynamical self-programming. Standard mathematics is ectomorphic, sorry. You proceed from a set of axioms or simple assumptions and then proceed gradually to more complex inferences. Mathematical philosophy, rather, is endomorphic, about the within of things and their internal structure. Mathematical philosophy proceeds from great complexity and seeks to discern the abstract relations characterizing this multiplicity of mathematical objects, thereby discerning the structure of the discipline itself and how this global syntax is topologically contained within every mathematical object, property, and relation. If mathematics is the study of quantity and space, mathematical philosophy is the study of mathematics. If initially mathematics and mathematical philosophy were one. In ancient Greece, many great philosophers were famed mathematicians, and vice versa. This is why you'll often hear, for instance, about Zeno's paradoxes. He was a Stoic philosopher who posed many problems that challenged the mathematical notion of a continuum by pointing out the contradiction in the idea of an infinitely subdividable interval. And the problems that he posed in both mathematics and philosophy continue to be debated to this day. Or Thales' theorem, which states that if you have a line cut straight across the circle between points A and C, the triangle connecting A and C and any point on the circle forms a right triangle. Thales was a pre-Socratic philosopher whom we discussed at length in our History of Western Philosophy course. The greatest and most advanced mathematicians in antiquity, like Zeno and Thales, were both mathematical philosophers. Finding axioms is philosophy, whereas using axioms is math. So and those used to be coupled, whereas now they're being put apart. But really, with our project of mathematical philosophy, we're bringing back together the within and without of things. So we are uniting mathematics back into a single unity. The standard series of natural numbers is 0, 1, 2, 3, and so on, adding by 1 all the way up to infinity. Technically, we should call this series, as we said, a discrete infinity because it does not have a continuous progression, but only has new values at intervals of 1. This is to differ it from continuous infinities without any jumps or breaks in their values, such as the number of points in between the ends of a line segment. In math, continuous infinities, such as the number of points in a line segment, are greater than discrete infinities, such as the amount of whole numbers. In Introduction to Mathematical Philosophy, Bertrand Russell points out that although we take the series of natural numbers for granted, it took eons probably in order for us bipedal apes to reach that kind of knowledge. Russell says it must have required many ages to discover that a pair of birds in a couple of days were both instances of the number 2. The degree of abstraction involved is far from easy to realize that 2 days and 2 birds are the same thing with respect to their number. So, and the discovery that 1 is a number must have been difficult. As for 0, it is a recent addition. The Greeks and Romans had no such digit. This is an unappreciated fact of number. We've gotten so used to abstraction that we forget the miracle of logico-mathematical thought. An entire syntax of human cognition, the logico-mathematical syntax, or LMS, probably lay dormant for the most part, only serving basic functions until formal abstract reasoning in mathematics really came into full swing in ancient Greece only a few millennia ago, where geometry, the syllogism, number theory, and formal metaphysics began. The moral of the story: don't take mathematics for granted, or even our ideas of number, space, and quantity, which we think of as pre-mathematical. And even if you ask the most advanced mathematicians, they may struggle to give you a decent definition of what any of these things are that they're supposedly experts in. For example, ask them to define a number. What is a number? Numbers are the things we do equations with. Sure, they might say, but what are those things? What connects 2 birds in 2 days? What is 2 actually? The simplest way to define a number is to use 5 statements utilized by Italian mathematician Giuseppe Peano. 0 is a number. The successor of any number is a number. No 2 numbers have the same successor. 0 is not the successor of any number. Any property which belongs to 0 and also to the successor of every number which has the property belongs to all numbers. Russell says, taking any number m, we define m plus 0 as m, and m plus n plus 1 is the successor of m plus n. In virtue of 5, this gives the definition of the sum of m and n, whatever number n may be. Any elementary proposition of arithmetic can be proved by means of our 5 premises. And if you have any difficulty, you can find the proof in Peano. This defines all numbers into existence with shared structure and properties, relying along with the operation of addition based on only 3 primitive ideas to be defined: 0, number, and successor. We can define 0 as a number, 1 as a number because it's the successor of 0, and so on. 10 million and 1 is a number because it is the successor of 10 million, meaning it shares the same properties and belongs to all numbers, including 0. Unfortunately, while this defines all natural numbers as being included within our descriptions, it leaves more questions than answers. What is 0? What is a number? What is a successor? To illustrate the absurd character of this definition, that would be like if a 4-year-old asked you what the CEO of Google was, and you said Eric Schmidt is a CEO of Google. The successor of any CEO of Google is a CEO of Google. No 2 CEOs of Google have the same successor. Eric Schmidt is not the successor of any CEO of Google. Any property which belongs to Eric Schmidt and also the successor of every CEO of Google that has the property belongs to all CEOs. This is the beginning of the definition, but I have to tell you who Eric Schmidt was, what a CEO is, what are the properties that are shared by every single CEO, such as being in charge of the business, running operations, and so forth. Similarly, our definition of the series of natural numbers assumes that we already know the definition of not only number, but also a successor and the number 0. Although all the axioms are true, they are not helpful or explanatory. They're descriptive more than prescriptive. The problem with Peano's axiom is that, as Russell says, that Peano's treatment is less final than it appears to be. Peano's 3 primitive ideas, namely 0, number, and successor, are capable of an infinite number of different interpretations, all of which will satisfy the 5 primitive propositions. Examples include defining 0 as 100 and number as all numbers greater than or equal to 0. Under this definition, 99 is not a number per proposition 4, which says that 0 is not the successor of any number. Obviously, any number can be substituted for 100, making the definition of our series essentially meaningless without first defining 0. All of Peano's premises are still satisfied in this definition. Keep the usual definition of 0, but define number as only multiples of 2, what we usually call even numbers. The series of natural numbers is now 0, 2, 4, 6, 8, all of Peano's premises still satisfied. If you define successor as half the previous term rather than that term plus 1, the series of natural numbers is 1, 1/2, 1/4, 1/8, etc. All of Peano's premises still satisfied. Russell says that given any series of terms which is endless, contains no repetitions, has a beginning, and has no terms that cannot be reached from the beginning in a finite number of steps, we have a set of terms verifying Peano's axioms. Peano's axioms are necessary but not sufficient to define the series of natural numbers. It does not add anything to our knowledge of the particular series that we aim to define. We need to independently understand the terms zero, number, and successor for Peano's definition of the natural number series to work or be meaningful. A number is something which characterizes collections, namely those which have that number. In this presentation, we'll define zero, number, and selection, number, successor, and zero using Russell's mathematical philosophy combined with the CTMU interpretation. The definition requires a definition of similarity. One class is said to be similar to another, Russell says, when there is a one-to-one relation of which the one class is the domain while the other is the converse domain. What we do when we count, say, 10 objects is to show that the set of these objects is similar to the set of numbers 1 to 10. For example, we know that the same number of natural numbers as there are in the series 1 over 2 to the n from 0 to infinity, because the series 1 over 2 to the n has exactly one value for every value n in the series of natural numbers. So 1 in the 1 over 2 to the n series is similar to 1 in the natural number series. 1/2 is similar to 2, 1/3 is similar to 3. So we know that there are the same number of fractions where 1 divided by n as there are numbers n, because you can put 1 for each one. 1 over 1, 1 over 2, 1 over 3, 1 over 4. 1, 2, 3, 4. We have an equal amount of both series, and so on, proving that the two classes are similar. Russell says, we may thus use the notion of similarity to decide when two collections are being made to belong to the same number. We want to make one bundle containing the class that has no members. This will be for the number 0. Then we want a bundle of all the classes that have one member. This will be for the number 1. Then for the number 2, we want a bundle consisting of all coupled, then one of all trios, and so on. Given any collection, we can define the bundle it is to belong to as being the class of all those collections that are similar to it. Yet, this in no way conflicts with the definition offered earlier, where he says a particular number is not identical with any collection of terms having that number. The number 3 is not identical with the trio consisting of Brown, Jones, and Robinson. It is a matter of logical priority. The logical relationship among Brown, Jones, and Robinson is similar to the bundle consisting of all trios and defined by the logical relationship 3. But the bundle consisting of all trios, 3, is not defined by any particular instance of the number 3, such as the trio Brown, Jones, and Robinson. This is a subtle distinction. So there are 3 people in that trio, but 3 does not equal that trio. Like 3 is not defined based on any particular instance of 3 objects. It's defined as the similarity relation between any sets of 3 objects. So therefore, the number 3 is a syndiphyonik relationship with both a synetic aspect, the number 3, and a diffeonic aspect, any possible trio. Russell writes, we naturally think that the class of couples, for example, is something different from the number 2, but there is no doubt about the class of couples. It is indubitable and not hard to define, whereas the number 2, in any other sense, is a metaphysical entity about which we can never feel sure that it exists or that we have tracked it down. It is therefore more prudent to content ourselves with the class of couples, which we are sure of, than to hunt for problematical number 2, which we must always remain elusive. Therefore, the number 3 is a syndiphyonik relationship with both a synetic aspect, the number 3, and a diffeonic aspect, any possible trio. Russell writes, we naturally think that the class of couples, for example, is something different from the number 2, but there is no doubt about the class of couples. It is indubitable and not difficult to define, as we just said. And we need to really focus in on that line. It's indubitable and not difficult to define. That's actually not exactly true, because we require a metaphysical definition, as Russell says we don't want, in order to actually define number precisely. It needs to be something that is not bound to the actual truthful content of any particular instantiation of it, but it's not just the class of all numbers too. 2 actually has to have a transcendent definition and ultimate character aside from that collection. So accordingly, Russell sets up the following somewhat logically problematical definition of a number, where he says the number of a class is the class of all those classes that are similar to it. A number is anything which is the number of some class. But what is Russell's a priori aversion to defining the number 2 as a metaphysical entity? Russell was committed to a dogmatic form of atheism called metaphysical naturalism, which, as against its name, ironically, says that nature is self explanatory and that all metaphysics is sloppy, imprecise, and irrelevant to the natural world. Russell's definition is not quite as unappealing as it seems, however. Russell was, after all, among the most intelligent men and finest logicians in human history. He explains definitions of this sort are, in fact, very common. The class of fathers, for example, would have to be defined by first defining what it is to be the father of somebody. Then the class of fathers will be all those who are somebody's father. In the CTMU, however, this semicircular definition is not enough. In the CTMU, number is not defined platonically, but as an algebraic representation of that number. So, for example, Langen says 0 is an algebraic representation of nothing in human cognitive perceptual syntax. So, for that matter, is the word nothing. It requires a mind in which to exist. Hence, it is not capable of existing alone and is therefore not really nothing. It's part of an irreducible mental coupling of nothing and something, as in nothing is the absence of something. Therefore, we arrive at a syntactic definition of 0 that translates to 0 syntactic constraint, with each new number on the number line binding this potential. So it's the self-binding of 0 and the self-restriction of infinity that creates the natural number sequence, which iterates from 0 to 1 to 2 to 3 to 4, all the way ad infinitum. So 2 is the representation of anything which is the number of some class of duos in human cognitive perceptual syntax. So the number 2 has external syntactic existence, but is irreducibly coupled with our cognitive syntax in order to exist or be registered in the mind as an internal reality. Numbers, yet again, are both a human construction semantically and a property of the intrinsic language of the universe as a collection of the set of all duos. This means that any definition of number must delicately couple mathematical Platonism, numbers that have a transcendent character, and nominalism, numbers that are described and created by humans, respectively corresponding to the intension, the definitional property, and extension, the definition of a number. Therefore, a concise definition of a number 7, for example, could be the representation of the intentional property of sets of 7 in the human cognitive perceptual syntax. It requires a mind in which to exist. Whether you define 7 as 7 things, or 1 times 7, or 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, all of these are equal to 7 in our own mind. So you can therefore think about a discrete infinity as a non-terminal sequence of 1, 2, 3, n plus 1, and so forth, all the way up forever. That's a non-terminal process because you can keep iterating it in that series forever. So you can define any number as the termination of that process corresponding to the number 7. That, for example, is the termination of the number of that series at n equals 7. A million is the termination of the infinitary n plus 1 series at n equals 1 million. This means that we can define a successor through the n plus 1 series operating through a discrete infinity. So every number is the termination of a discrete non-terminal process. So in a sense, infinity can be said to program or distribute over every single number as the non-terminal phase of mathematics. So 0 is an algebraic representation of nothing in human cognitive perceptual syntax, requiring a mind in which to exist as its start symbol, setting the whole natural series, the natural number series going, so to speak. Number is the representation of the intentional property of sets corresponding to that number. And succession is the n plus 1 series operating on a discrete infinity, terminating on the assigned value to the number. These three ideas form a comprehensive description of Peano's three primitive ideas, and therefore allow us to coherently define the natural number series and insert our definition into the CTMU. 0 is unbound structure. Succession is the non-terminal series with a discrete interval of 1, and number is the representation of the intentional property of sets corresponding to that number. As Langen says, at one time a number was a positive integer. As the years passed, new kinds of number were discovered: 0, negative numbers, rational numbers or fractions, irrational numbers that cannot even be expressed as fractions, complex numbers, and even transcendental and transfinite or infinite numbers. Noting that each kind of number is associated with an algebraic system like a number field, we finally realize that a number is an element of an algebraic system. Because the CTMU embodies an algebraic system called SCSPL, it too is numeric. And since this system is the basis of a proof of God's existence, the CTMU might be said to reveal the existence of God with numbers. God is a mathematician, and numbers are syntactic elements of the SCSPL operator algebra that play an agentive role in the construction of the universe through a combination of terminal, finite, and non-terminal, infinitary elements. Therefore, mathematics is metaphysics, and the two cannot be understood apart from one another. Once this role is understood, the mathematical realms will fall back together of their own gravity. Thank you. Let the light shine forth in the darkness. May the peace of our Father in heaven be upon you. Like and subscribe. Peace.